this itself. I would like to give you one more little comforting magnitude vectors. So I broke it up in that manner. And then I broke it up again as the diagonal of that square. So this is clearly a quarter octahedron. You agree there's a quarter of an octahedron. Here is the equilateral triangle which was on the face of the octahedron. I'm going to just sit it down here. You'll find that this equilateral triangle must be congruent with that equilateral triangle of the tetrahedron. It also has an equilateral triangular base, which is part of these are the same vector edges. So it has exactly the same base as the tetrahedron, hasn't it? It has the same base, it has the same altitude. Can't help it. Therefore, its volume must be the same. The volume then of one tetrahedron and one quarter octahedron are the same, therefore an octahedron has 4 times the volume of the other tetrahedron. This is where you simply go back to the old x, y, z coordinates to the multiplication of the tetrahedra can look to us. We look at them in terms of they're looking like this, they can look like this, they can look like this, and they can look like this. As here I have the vector edge, here I have the face, here I have the vertex, so the main topological aspects. And this one reminds us that we only have approximation, that the vectors don't actually go through the same points at the same time, but they get into what we call their critical proximities, and the critical proximities do bring about certain energy behaviors which give us certain unique frequencies. We get adherence as we get into highly critical proximities, and apparently our experiences show us some kind of gravitational energy chemical element where we're all isolated, and after which men, having found the chemical element, I've got some pattern there, and I'm going to count up. You have to make some judgments with me. Inside here, there's a little tiny triangle. There's an area in there. You see? So I'd say that's an area. I'm going to count up all the vertexes. In order to distinguish them, I'm going to put up a little orange on every vertex. 1, 2, 3 here. 1, 2, 3 there. So we're going to count up the numbers of vertexes. It will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33. This is, I'm not sure where this is from. I said 33, didn't I? Under V. Now, he says the numbers of vertexes plus the numbers of faces equals the numbers of edges plus the number 1. So I'm going to count up the numbers of faces. There's one little tiny one inside here, into those 3. 1. I'm going to put a color in so it's hit mark. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. number of edges, and so what this says is that we ought to get the number of edges ought to be 1 and 6, 61 edges. So we try them out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 41, 42, 43, I'm going up 45, 44, 45, 46, 47, 48, 49, 50, 51, should that add up to 51? No. I seem to be very far shy. Be careful. I've ever found it to be wrong, and nobody else has. And so I'm very confident of his pattern. I'll make a fairly simple one, so that we won't have make a tetrahedron really quite high out in altitude, and I can get it flatter and flatter. So finally, somebody's going to look like this. And you can't seem to see any altitude at all. Here's to say something about Euler. When he said that when we're dealing in geometries that are not flat, that the numbers of vertexes plus the numbers of faces equals the numbers of edges plus the number 2. There's some exceptions to these that you'll come to. As there's a hole in it, then it's going to be something else again. But if it's in the round and you don't deal in special holes in it, then the numbers of vertexes are number of faces. So you take, for instance, the cube. Cube, our friend, equals 6, equals the number of edges, which are 12, plus 2. 14 equals 14. We do it with a tetrahedron. Tetrahedron is 1, the number of vertexes, 4, plus the numbers of faces, 4, equals the number of edges, which are 6, plus the number 2. 8 equals 8. The octahedron has 6 vertexes plus 8 faces equals 12 edges plus the number 2. And the rhombic dodecahedron there has plus 12 faces equals number of edges. 1, 2, 3, 4, 5, 6, 7, 8, 9. The 9 in this top cap, the 9 in the bottom cap, 18, and around the edge, 1, 2, 3, 4, 5, 6. So that's 24. So that's right, equals 24. Totally wrong. That's that count. 1, 2, 3, 4, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 7. That's what that was 7. There's 7 in this north pole and 7 in the south pole. Opposite pole is here. 7 in the south pole. So there is 14 vertexes. 14 vertexes plus the 12 faces equals 24 edges plus 2. Let's take an asymmetrical one, such as this, for instance. Start off with, it does have its 4 faces and 6 edges and 4 vertexes. But when I get my tetrahedron so flat that it looks like a plane triangle when the altitude is reduced, then the top 3 faces of the tetrahedron, this one here, 1, 2, and 3, are now congruent with the base. So that this one, 1, 2, and 3 are congruent with number 4, which is the whole thing, which is the base. Therefore, you dropped out one face. You dropped out 1 on this side of the equation. Therefore, I have to take out 1 on this side of the equation. So it will equal B plus F equals E plus 1. In other words, when a form looks as though it was flat, it looks like it's a plane, you and I have now learned, by virtue of coming from total universe into the first subdivision in the universe in order to be thinkable, into its being a tetrahedron. Now, you and I will agree that a tetrahedron can, you and I can look at the tetrahedron, and I'm going to put a triangular hole inside of that. I'll do the hole in here in yellows. Now we do our counting of this one. How many faces have I got? I've got on the outside here, we've got 3 main faces of the prism. 3 F's. This is a counting of F. Then I have in the top here a face here and a face here in the bottom. 2 more faces. Then I have inside 3 faces. 1, 2, and 3. Total of 8 faces. So F equals 8. Now we know the vertexes are 1, 2, 3, 4, 5, 6, and 6 down here. So there are 12 vertexes. 3 comes first. 12 vertexes plus 8 faces. And that should, how many edges do you get? You get 1, 2, 3, 4, 5, 6 on the top, 6 on the bottom. Just counting up there, 6 at the top and 6 on the bottom. And then we have 1, 2, 3 on the outside, 1, 2, 3 on the inside, a total of 6 internally. 6, 6, 6, 18. Have I done it correctly? Now we can do this one over again. Here we have numbers of the vertexes are 1, 2, 3, 4, 5, 6, and the numbers of faces are external vertical face, which is the white one here, the prism, and there's three of those external prism external faces, 3 of those, and three internal yellow faces, which are like that, these belly ones. So there's six faces in the system. And then the numbers of edges are 3 on the top, 3 on the bottom, making 6, plus 3 whites vertically, and 3 yellows vertically, making 6 again, making a total of 12. So when there's a hole, when we polarize the system, when we give up one of the faces and turn the pair of the opposite faces into holes and run a hole through, this is the way we make a donut. When we do that, then the numbers of vertexes plus number of faces equal the numbers of edges. They don't have to add anything. What you discover there is that before you put the hole in the cube, you did away with 2 of the faces and made them holes, leading through to the other ones. You can do that simply by just taking a cube and throwing away the top and the bottom faces, then you will have the internal faces are now exposed to the system as well as the external, which will be the same as my orange one. As you just look at the inside of the face, and you paint the inside a different color, and you have the right to, so there'll be the blue face on the inside, and the yellow face on the outside, and then the holes here, so those are not faces, but they're holes. And when you consider them as holes, and put the hole clear through the system, you polarize it. That is, you knock out the top and the bottoms, which were the poles, the North Pole and the South Pole. And or you core it the way you would an apple. And when you do that, we lose the +2. So we have the condition of when it is in the round, it comes out always +2. When we flatten down this thing, it looks like a +1 because we lost one of the faces. And we only see the North Pole. And then when we put the hole through it, we take out the North and the South Poles themselves and just have a core through it, and therefore we lose this tube. This may be suspicious that the two-ness related to something I call poles. And I began to play a game of topology that way, and I can't get 6 triangles around a vertex because if I did, then those triangles would be, if it is symmetrical, they are equilateral, they would be the hexagon, and this will add up to 360 degrees, which is infinite, and the system will never come back upon itself. The minimum that I can have in a system, which in order to be able to divide the universe into within this and without this, which means it must return upon itself, we require a convexity or a concavity. Concavity is seen from within, or convexity is seen from without. And the fiveness is the last case of equilateral omnisymmetry triangulation. There turn out to be then, there's 3 possible cases, tetrahedron, octahedron, and icosahedron, of omnitriangulated symmetry, which will subdivide the universe into withinness and withoutness. And quite clearly, in the case of the tetrahedron, I take four faces to get one volume, unit of volume. In the octahedron, I take only 8 faces, which is twice as many faces, but I get a volume of 4. I'm getting twice as much volume for a given face. In the case of the icosahedron, I'm getting, out of only 20 triangles, I'm getting approximately 20 volumes. That is, each face is giving me a unit of volume. In the tetrahedron, I only get a quarter of a unit of volume out of the 4 faces. I'll draw it this way. Spherical icosahedron is simply taking the regular icosahedron and putting a light inside of it and projecting it onto a sphere. So we get arcs for each one of these chords. This is spherical icosahedron. You're looking at this aspect of the system. The angles around here add up to 360 degrees. 360 degrees, 360 degrees. There are only 5 of these triangles that come together spherically. So 5 into 360 degrees means that each one of these angles must be 72 degrees. So this is 72 here, this is 72 here. 72, each one of those is 72 degrees. When I do the spherical trigonometry on a triangle in here, we discover that these angles in here are about 63 degrees. 63, 63. This one here is be 180, so 63 from 180, 117, and then divide that into 2, and we get 5, and approximately 55 and 58. Each one of these angles here is approximately 58 and a half degrees, 58 and a half degrees, 58 and a half, 58. Otherwise, right in here there's a spherical triangle, 72 degrees, 58, 58, 63, 63, 63. This is an isosceles spherical triangle in here, and this one here is an isosceles spherical triangle, 72, 53, 58, 58. So these are different triangles. Spherical triangles, we have to help every student who's ever grown up down here and around and back into the South Pole. We know it impinges here at 90 degrees. because that's the way we cut it. This is the axis of the Earth, and this equator is a plane that's perpendicular to the Earth's axis, so the plane, this great circle plane, must impinge on this plane at 90 degrees here. So this is a 90-degree impingement of this meridian on the equator. I'm going to go 1/4 away around the Earth, which brings me over to here, on the equator. Now I'm going to return to the North Pole on a meridian. And I've left it, this meridian must have impinged it on here at 90 degrees also. And when I look down on the North Pole, that's what I did. I started the North Pole, went down to the equator, went 1/4 away around the Earth, which is to here, and back up. This must be 90 degrees here. That's what we said, 1/4 way around the Earth is a quarter. So each one of these angles is 90 degrees. Therefore, 90, 90, 90 equals 270. So the sums of the angles of that spherical triangle, where it's a spherical often, are 270 degrees. Once you know that in spherical trigonometry, the angles never on one, the six squares, and the 8 triangular facets are showing. If I contract that center ball, we have a model, and my model broke down on me, so I can't use it to show it to you. I have little rubber bands, and I pull the central red ball out, and the rubber bands between all the external ones. And the minute I do that, then the squares here immediately, because we know that squares of balls are uncomfortable, and they want to get some kind of a nesting condition. And this ball could move towards this one here. They could roll on one another, or this one could move towards this one. And not until one or the other has occurred does this become stable. And when it does occur, then we will have this ball like that, and then there's one in here and one in here. We have, in effect, really this triangle or this triangle. It makes a diamond. Now these are closely packed. And the altitude between here and here, the base is the same. This distance stays the same, this stays the same, but the altitude of the triangle is less than the altitude of the square, so that these are more closely packed. What happens when I knock the ball out of the center or let it reduce in size is that every one of the squares immediately collapses so that this ball nests on here. And that is the icosahedron. The icosahedron is the same 12 vertexes as the vector equilibrium, which we've now learned about. And I can say that it's interesting then that there are, for instance, in the icosahedron, there are 20 in vertexes, 12 vertexes. 1, 2, 3, 4, 5, 6 in this hemisphere, 6 in the other hemisphere. 12 vertexes, 20 faces. 1, 2, 3, 4, 5, 6. This one here, this distance from here to here, and this increment here and this increment here are the same distances. I'll have to just divide those. There are 10 such increments around here. Therefore, this little tip of a triangle here will fit onto this truncated part of a triangle here. This part here fits onto this one, and they form one complete triangle. So we see in this hemisphere 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 triangles in this hemisphere, 10 in the other, 20 triangles altogether. So there are 20 faces, and there are 30 edges, plus 2. 1 edge, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is a half an edge, 11, 12, 13, 14, 15 edges in this hemisphere, 15 in the other hemisphere, 30 altogether. 30 plus 2. So B equals F. 3 plus F equals B plus 2. 30. So there are 30 edges in the system. Now then, there are 12 vertexes, there are 20 faces, there are 30 edges. Now, in relation to an edge or a vertex, there really represent the domains of the edges of the icosahedron. And there will be 30 such diamonds. And you can divide the whole system into 30 areas instead of 20 areas, or 12 areas, then you have the lowest common denominator. And the fact is that these 30 diamonds do represent the lowest common, the largest number of subdivisions I can make, except for the fact that I can also notice within this diamond right here, there are 30 of these that make up the sphere. There is this line crossing here, which we got from the dodeca. When we combine the dodeca and the icosa, we then get this diamond, and we'll extract it and look at it out on the side. Here it is, right here. It has 1, 2, 3, 4 right triangles within it. And because it's concave, the system is concave from the inside. The concave and the convex are not the same. So this one is positive, this is negative, and this is positive, and this one is negative. Otherwise, they're the same. Their edges are identical lengths, their angles are the same. But one is positive, there are 2 positives and 2 negatives. And so the positive one I'm going to make solid like that, and there's another positive in here. So it's a checkerboard. So I've got 120 of these, 30 times 4. This divides into 4. So, and there are 30 of these diamonds per sphere. Therefore, there's 120 of these triangles that subdivide the system. I can tell you that in omnitriangulated symmetry, this is the largest. What is the dodecahedron? You now recognize in a minute. And so I'm going to have to put a triangular diagonal on each. So dodeca has 32 vertexes. And how many faces? It has. These faces are these 60 triangles I talked about, so there'll be 60 of them. Remember the 60 is that domain of the diamond breaking into this, a 2-frequency geodesic. So each of these faces, what we call the triangulated dodeca is simply the 2-frequency geodesic. So there are 12 of these cases times 5. There are 60 of those triangles. 60 faces. Then how many edges? There are, all the edges are, there are 30 of these which cross that diamond there. And there are, up here, so this will read 2. I take 2 and put it over here in the head of the formula. So I've got this bracket for all of these units. So 2 P's. 2 PBs. These are vertexes which are poles. And now, so this will read 2, and this one will read here will read 4, and this one here will read 6, and this one here will read 12, and this one here will read 10, and this one here will read 10, and this one here will read 30. Right? Now, the rest of the formula stays the same. There'll be plus 4 faces, 8 faces, plus 12 faces, plus 24 faces, plus 20 faces, plus 20 faces, plus 60 faces. Equals 6, equals 12, equals 18, equals 36, equals 30, equals 30, equals 90. Because I've taken the two out over here, so I can eliminate the 2 on this side, quite obviously, because I have somebody just balancing the formula. So now I have a series, as due to the fact that I've shown you that I could second power by triangling, that is when I increase the frequency of the geodesic structure, the icosahedron, or I could triangulate the octahedron, or I could triangulate the tetrahedron to start off with, but I found I got the most symmetry by doing it with the icosa. The point is I could do it at any of them. I could do, every time I do, then, supposing I make it a 4-frequency structure, you and I have now learned by actual models that the 4-frequency is simply the second power of it. Therefore, frequency is second powering. Therefore, I can omnitriangulate any one of these simply by taking frequency, and the symbol for frequency in mathematics, physics is the letter nu, the Greek letter nu, so like that, to the second power. So I can now give you a formula which is And I took the sum of the angles of the octa. And the octa has 6 vertexes, and she has, in the 6 vertexes, she has 4 times 60 degrees at each vertex, which is 240 times 60. And that'll be 1,440. All right? 14,400. That's great. Oh, 6 vertexes, excuse me, 6 vertexes. 1,440. You agree on that? I don't that I may. That you might be one little sphere that's floating around in the universe. And if you found another sphere, you could cuddle up to it, all right, and you could keep rolling around on each other. You'd be very free to roll around. And the two of you could go on very freely all around through the universe, just rolling around. But you would look like, to anybody looking at you from far away, they wouldn't know you're rolling around in one another, and you'd look like you're just in tendency. That's all. That's the big profile anybody would see. And then they're stabilized. So I can take 3 and 3, which is a very fundamental kind of a coupling. Then I can, if I bring them together like this, they're very unstable. But if I bring them together, again, precession, I will preset smiley, and they're now nest. So you can see 3 valleys in here, and these 3 fit in there very neatly. And this gives me 6 balls, and you begin to count up, you see 8 triangular faces. This is the octahedron. In other words, the octahedron has 6 vertexes. You don't really kind of get used to looking at this as an octahedron, but there it is. It is the octahedron. And it has an interior, and you can look at it, it's fairly good little space inside there. So there are 2 kinds of interiors of agglomerations, the octahedron and the tetrahedron. Much there are 4 balls, each has a triangular window, a triangular hidden piece of the ball between the points of contact. And there are 4 triangular windows and 4 balls. There are 8 triangular faces that are involved. And that gives us the 8 is the octahedron, and here is exactly one of those faces. We'll glue those balls together and take a razor and cut very carefully between the points of gluing, and you get a little octahedron, which is a concave octahedron. You see? And we can make the 4 balls just nest on there very neatly. Two nests here, and the other 2 nests here. There they are. That is the space that's in there. Then, what kind of space you got in here? Well, we see it's an octahedron, and an octahedron has a square aspect like that. So that ball